Hello. So here I am with my Google account already opened. And last time we left the situation in a really different way. We were fourth in the Golden League, and it's just about 1 hour to get the promotions to the Diamond League. So let's go and let's make some points so we avoid that these two guys here may make it above us. Let's go. Therefore, I was here in Elastic Cloud
Cloud
infrastructure.
CDN or Content Delivery Network uses Google's globally distributed edge points of presence to cache HTTPS
Okay, so just to quickly understand what we are doing, we are finishing this module called load balancing and auto scaling. It's just about some other videos and one lab. So let's see if we can bring home this more than 100 points and be sure
load
to
balancer
pass to the
content close to your users.
Diamond League.
Specifically, content can be cached at CDN nodes as shown on this map. There are over 90 of these cache sites spread across metropolitan areas in Asia Pacific, Americas, and EMEA. For an up-to-date list, please refer to the Cloud CDN documentation. Now, why should you consider using Cloud CDN? Well, Cloud CDN caches content at the edge of Google's network, providing faster delivery of content to your users while reducing serving costs. You can enable Cloud CDN with a simple checkbox when setting up the backend service of your HTTPS load balancer. So, it's easy to enable and benefits you and your users, but how does Cloud CDN do all of this? Let's walk through the Cloud CDN response flow with this diagram. In this example, the HTTPS load balancer has two types of backends. There are managed VM instance groups in the US Central 1 and Asia East 1 regions, and there is a cloud storage bucket in a US East 1. A URL map will decide which backend to send the content to. The cloud storage bucket could be used to serve static content, and the instance groups handle PHP traffic. Now, when a user in San Francisco is the first to access a piece of content, the cache site in San Francisco sees that it can't fulfill the request. This is called a cache miss. The cache might attempt to get the content from a nearby cache. For example, if a user in Los Angeles has already accessed the content. Otherwise, the request is forwarded to the HTTPS load balancer, which in turn forwards the request to one of your backends. Depending on what content is being served, the request will be forwarded to the US Central 1 instance group to the US East 1 storage bucket. If the content from the backend is cacheable, the cache site in San Francisco can store it for future requests. In other words, if another user requests the same content in San Francisco, the cache site might now be able to serve that content. This shortens the round trip time and saves the origin server from having to process the request. This is called a cache hit. For more information on what content can be cached, please refer to the documentation. Now, each Cloud CDN request is automatically logged within the Google Cloud. These logs will indicate a cache hit or cache miss status for each HTTPS request of the load balancer. You will explore such logs in the next lab. But how do you know how Cloud CDN will cache your content? How do you control this? This is where cache modes are useful. Using cache modes, you can control the factors that determine whether or not Cloud CDN caches your content by using cache modes. Cloud CDN offers three cache modes, which defines how responses are cached, whether or not Cloud CDN respects cache directives sent by the origin, and how cache DTLs are applied. The available cache modes are use origin headers, cache all static, and force cache all. Use origin headers mode requires origin responses to set valid cache directives and valid caching headers. Cache all static mode automatically caches static content that doesn't have the no store, private, or no cache directive. Origin responses that set valid caching directives are also cached. Force cache all mode unconditionally caches responses, overriding any cache directives set by the origin. You should make sure not to cache private per user content such as dynamic HTML or API responses.
Let's talk about SSL proxy and TCP proxy load balancing. SSL proxy is a global load balancing service for encrypted, non-HTTP traffic. This load balancer terminates user SSL connections at the load balancing layer, then balances the connections across your instances using the SSL or TCP protocols. These instances can be in multiple regions, and the load balancer automatically directs traffic to the closest region that has capacity. SSL proxy load balancing supports both IPv4 and IPv6 addresses for client traffic and provides intelligent routing, certificate management, security patching, and SSL policies. Intelligent routing means that this load balancer can route requests to backend locations where there is capacity. From a certificate management perspective, you only need to update your customer-facing certificate in one place when you need to switch those certificates. Also, you can reduce the management overhead for your virtual machine instances by using self-signed certificates on your instances. In addition, if vulnerabilities arise in the SSL or TCP stack, GCP will apply patches at the load balancer automatically in order to keep your instances safe. For the full list of ports supported by SSL proxy load balancing and other benefits, please refer to the link section of this video. This network diagram illustrates SSL proxy load balancing. In this example, traffic from users in Iowa and Boston is terminated at the global load balancing layer. From there, a separate connection is established to the closest backend instance. In other words, the user in Boston would reach the US East region, and the user in Iowa would reach the US Central region if there's enough capacity. Now, the traffic between the proxy and the backend can use SSL or TCP. I recommend using SSL.
Let's find out what SSL stands for. Transport layer security, but secure socket layers. So this is a cryptographic protocol designed to provide telecommunication security over a computer network such as the internet. The protocol is widely used in applications such as email, instant messaging, and voice over IP, but its use in securing HTTPS remains the most publicly visible. Okay, so but it's used in securing, okay. So the TLS protocol aims primarily to provide security, including privacy, integrity, and authenticity through the use of cryptography, such as the use of certificates between two or more communicating computer applications. It runs in the presentation layer and it is itself composed of two layers. Okay, the closely related datagram transport layer security is a communication protocol that provides. And TLS is a proposed Internet Engineering Task Force standard, first defined in 1999. Okay, TLS builds on the now deprecated SSL specifications. What the fuck? Since applications can communicate either with or without TLS or SSL, it is necessary for the client to request the server set up a TLS connection. Okay. One of the main ways of achieving this is to use a different port number for TLS connection. Port 80 is typically used to encrypted HTTP traffic, while port 443 is the common port used for encrypted HTTPS traffic. Another mechanism is to make a protocol-specific start TLS. Okay. Okay. And they were
TCP proxy is a global
mentioning...
load balancing.
Okay, so I will ask ChatGPT what goes through SSL proxies. Oh, my keyboard's not working as as I was expecting. What goes through SSL proxies? In GCP, it says it is not HTTP traffic or HTTPS traffic. So what do we exactly manage in these proxies? SSL proxies are designed to handle non-HTTP HTTPS encrypted traffic that uses the SSL TLS protocol. This distinction is important because SSL proxies are specialized for encrypted connections that aren't strictly HTTPS based. So here's a breakdown of what goes through SSL proxies, non-HTTPS encrypted traffic. SSL proxies can process traffic that uses encryption but isn't necessarily tied to the HTTP protocol. This includes protocols like WebSocket connections, encrypted database connections, custom application using SSL TLS for encryption, transport layer security only. SSL proxy load balancer is explicitly designed for workloads that rely on SSL TLS as the transport layer. It terminates the SSL TLS connection at the load balancer and forwards the decrypted traffic to the backend services. Okay. Are typically handed. Okay. Why provide? Unencrypted traffic. This would either pass through without decryption or require a different load balancing solution such as TCP proxy load balancer. Why use SSL proxy load balancer? SSL proxy load balancer is suitable when you need to offload SSL TLS processing from your backend services. Your application traffic isn't web-based but still uses encryption. You want a globally distributed load balancer to ensure low latency for encrypted non-HTTP traffic. Oh, I see. So, therefore, instead of using a simple TCP proxy, I will use SSL to for security reason. In TCP, we are not encrypting the packets. Correct, you're making a valid point about the difference between SSL proxy load balancer and TCP proxy load balancer. Here's a deeper look. At TCP level, the protocol itself does not inherently provide encryption. It is simply a transport layer protocol responsible for ensuring reliable delivery of packets. In encryption is required that if encryption is required at TCP level, it must be implemented by the application layer using protocols like TLS, SSL, which operate on top of TCP to secure the connection. So it will not be able to handle SSL termination. It's for packets as is between clients and backend instances. If you need encryption, your backend must handle SSL TLS. Okay, SSL proxy for security. So yeah, this is will start for the between the client and the load balancer without burning the backend server without encryption overhead. Okay. Why not use TCP proxy with application layer encryption? While you can still use TCP proxy and configure your backend to handle SSL TLS, this approach has limitations. Increased computational load on the backend instances, difficult to manage SSL certificates if you have many backends or frequently need to update them, no centralized control over SSL and TLS policies. So SSL proxy load balancer is a better choice when you want to centralize SSL TLS termination for security and offload the computational burden from your backend. Great, so now we have a better understanding.
Unencrypted non-HTTP traffic. This load balancer terminates your customer's TCP sessions at the load balancing layer, then forwards the traffic to your virtual machine instances using TCP or SSL. These instances can be in multiple regions, and the load balancer automatically directs traffic to the closest region that has capacity. TCP proxy load balancing supports both IPv4 and IPv6 addresses for client traffic. Similar to SSL proxy load balancer, the TCP proxy load balancer provides intelligent routing and security patching. For the full list of ports supported by TCP proxy load balancing and other benefits, please refer to the links section of this video. This network diagram illustrates TCP proxy load balancing. In this example, traffic from users in Iowa and Boston is terminated at the global load balancing layer. From there, a separate connection is established to the closest backend instance. As in the SSL proxy load balancing example, the user in Boston would reach the US East region and the user in Iowa would reach the US Central region if there's enough capacity. Now, the traffic between the proxy and the backends can use SSL or TCP, and I also recommend using SSL here.
Okay, so we're still in the promotion zone.
Let's talk about network load balancing, which is a regional load balancing service. Network load balancing is a regional, non-proxied load balancing service. In other words, all traffic is passed through the load balancer instead of being proxied, and the traffic can only be balanced between VM instances that are in the same region, unlike a global load balancer. This load balancing service uses forwarding rules to balance the load of your systems based on the incoming IP protocol data, such as address, port, and protocol type. You can use it to load balance UDP traffic and to load balance TCP and SSL traffic on ports that are not supported with the TCP proxy and SSL proxy load balancers. The architecture of a network load balancer depends on whether you use a backend service-based network load balancer or a target pool-based network load balancer. Let's explore these in more detail. New network load balancers can be created with a regional backend service that defines the behavior of the load balancer and how it distributes traffic across its backend instance groups. Backend services enable new features that are not supported with legacy target pools, such as support for non-legacy health checks, TCP, SSL, HTTP, HTTPS, and HTTP2, autoscaling with managed instance groups, connection draining, and a configurable failover policy. You can also transition an existing target pool-based network load balancer to use a backend service instead. But what is a target pool resource? A target pool resource defines a group of instances that receive incoming traffic from forwarding rules. When a forwarding rule directs traffic to a target pool, the load balancer picks an instance from these target pools based on a hash of the source IP and port and the destination IP and port. These target pools can only be used with forwarding rules that can handle TCP and UDP traffic. Now, each project can have up to 50 target pools, and each target pool can only have one health check. Also, all the instances of a target pool must be in the same region, which is the same limitation as for the network load balancer.
I'm not 100% sure about that.
Next, let's talk about internal load balancing.
Pools.
The internal TCP UDP load balancer is a regional private load balancing service for TCP and UDP based traffic. In other words, this load balancer enables you to run and scale your services behind a private load balancing IP address. This means that it's only accessible through internal IP addresses or virtual machine instances in the same region. Therefore, you configure an internal TCP UDP load balancing IP address to act as the front end to your private backend instances. Because you don't need a public IP address for your load balance service, your internal client requests stay internal to your VPC network in a region. This often results in lowered latency because all of your load balanced traffic stays within Google's network, making your configuration much simpler. Let's talk more about the benefits of using a software-defined internal TCP UDP load balancing service. Google Cloud internal load balancing is not based on a device or a VM instance. Instead, it is software-defined, fully distributed load balancing solution. In the traditional proxy model of internal load balancing, as shown on the left, you configure an internal IP address on a load balancing device or instances, and your client instance connects to this IP address. Traffic coming to the IP address is terminated at the load balancer, and the load balancer selects a backend to establish a new connection to. Essentially, you have two connections, one between the client and the load balancer, and one between the load balancer and the backend. Google Cloud internal load balancing distributes client instance requests to backends using a different approach, as shown on the right. It uses lightweight load balancing built on top of Andromeda, Google's network virtualization stack, to provide software-defined load balancing that directly delivers the traffic from the client instance to a backend instance. For more information on Andromeda, see the link section of this video. Now, Google Cloud's internal HTTPS load balancing is a proxy-based regional layer 7 load balancer that also enables you to run and scale your services behind an internal load balancing IP address. Backend services support HTTP, HTTPS, and HTTP2 protocols. Internal HTTPS load balancing is a managed service based on the open source Envoy proxy. This enables rich traffic control capabilities based on HTTPS parameters. After the load balancer has been configured, it automatically allocates Envoy proxies to meet your traffic's needs. Now, internal load balancing enables you to support use cases such as the traditional tree-tier web services. In this example, the web tier uses an external HTTPS load balancer for use cases such as the traditional tree-tier web services. In this example, the web tier uses an external HTTPS load balancer that provides a single global IP address for users in San Francisco, Iowa, Singapore, and so on. The backends of this load balancer are located in US West 1, US Central 1, and Asia East 1 regions because this is a global load balancer. These backends then access an internal load balancer in each region as the application or internal tier. The backends of this internal tier are located in US West 1A, US Central 1B, and Asia East 1B. The last tier is the database tier in each of these zones. The benefit of this tree-tier model is that neither the database tier nor the application tier is exposed externally. This simplifies security and network pricing.
Okay.
Let's apply some of the internal load balancer concepts that we just discussed in a lab. In this lab, you create two managed instance groups in the same region. Then you configure and test an internal load balancer with the instance groups as the backends as shown in this network diagram.
Okay. Let's go. Let's start. Oh, your last lab was ended because you did not follow the lab instruction. As a reminder, repeat behavior may result in an account block. What? No way. I completed everything. What? I have my subscription. Your subscription. I have videos proving that I did everything. You cannot trick me, unless considering that you have my videos. Okay. So, while we're waiting for this, maybe just in a few minutes we'll receive the promotion. I hope they do not do new points right now. Come on. This is strange. Okay, so we obtained it. Nice. Want everything in English. And here we have Windows Capture Dashboard. Okay. Yeah, let's continue like this. Great. So configure an internal traffic and health check firewall rules. Configure firewall rules to allow internal traffic connectivity from sources in this range. This rule allows incoming traffic from any client located in the subnet. Health checks determine which instances of a load balancer can receive new connections. For application load balancing, the health check probes to your load balanced instances come from addresses in the range, blah, blah, blah. Your firewall rules must allow these connections. Explore the My Internal App network. The network My Internal App with subnet A and subnet B and firewalls for RDP, SSH, and ACMP traffic have been configured for you. So go to VPC, notice the My Internal App network with its subnets. Each Google Cloud project starts with the default network. In addition to My Internal App network has been created for you as part of your network diagram. You will create the managed instance group in subnet A and subnet B. Both subnets are in the US East 1 region because an internal network load balancer is a regular service. Okay. The managed instance group will be in different zones, making your service immune to zonal failures. So create the firewall rule to allow traffic from any sources. Let's go. What the fuck? So create firewall rule. Okay, now I can do something. They did everything for me. So I will create this firewall rule called like this. Let's go VPC network firewall rules. So we already have app allow ICMP, app allow SSH RDP. Create firewall rule named like this. Network My Internal App. Okay. Specify target tags, backend service. So IPv4, this range, allow all. Make sure to include, yeah, and then create. So create the health check rule. In firewall, create firewall rules. Okay, so this was the create the firewall rule to allow traffic from any sources. Then create the health check rule. Firewall allow health checks. Internal app targets backend service. IPv4, these ranges, and this range. Specified protocols and ports, okay. So make sure to include the ranges, okay. For TCP, check the box and specify 80. Then click create. Great, now we have both these firewall rules, which will allow the health check rule, the health check to pass, and traffic from this IP range. Now create a NAT configuration using Cloud Router. Create the Cloud Router instance. So network services, Cloud NAT, okay. Network services, Cloud NAT. So get started, and this will be the name of the gateway. It will be my internal app US East 1. Region US East 1. And click route router and select create new router for name type, not router US East 1. So the name will be this one, then create and create. Where the fuck is the other create? Here. Okay, running. So check. Let's go. Configure instance templates and create instance groups. Configure instance templates and create instance group means going to VM instances, notice the instances that start with instance group 1, instance group 2. Select SSH button next to instance group 1 to SSH into the VM. If prompted, allow SSH, blah, 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 run the following command to rerun the instances startup script. So we go here in Compute Engine VM instances. We go to this one, the group 1. We'll share with you the third window. Authorize. Now we go with sudo Google metadata script runner startup. So it's obviously a variable which has sense here. Startup, it's an argument. Let's go. So Google metadata script runner is obviously a command installed here. Then repeat the previous step for instance group 2. Okay, so we need to do it here too. Authorize. Let's go. So this one has finished. Wait for both startup scripts to finish executing, and then close the SSH terminal to each VM. The output of the startup script should state the following. Verify the backends. Okay, to verify the backends, we navigate to VM instances. Their instances are separated in zones and their internal IP addresses are part of subnet A and subnet B. Create instance and we'll create utility VM. Okay. US East 1, US East 1B. And then Series E2 medium. Perfect. So we have everything done. Advanced option, networking interface. And specify the following. So we will create another. We'll assign my internal app network. Yeah, add a network interface to my internal app. Yeah, subnet A. Perfect. Ephemeral custom IP address. So ephemeral custom ephemeral IP address. External IPv4 address known. done. Okay, then create. Note that the internal IP address for the backends are 10.10.22 and 10.10.32. If these IP addresses are different, replace them in the two curl commands below. Check my progress. Great. It says it's done. For utility VM, click SSH to launch the terminal and connect. To verify the welcome page for instance group 1, run the following command. Okay, so yeah, this is the internal IP. And we'll run a command to ask the welcome page of the instance group. We're having some issues today with the authorizations. Yeah, not only authorizations, yeah, a bit of everything. So let me share with you this page, which is taking forever. Let's see. So let me see one thing, because I put no external IP address. Oh, well, it's using the external IP address from where? I don't understand. Let's try another time. Authorize. Oh, now it worked. Okay, so the command was curl and the internal IP. Okay, so this is this piece of HTML. Great. Sometimes, yeah, I just to verify the welcome page, for instance, too. Yeah, so I run the same basically. And I should receive the same, right? Which of these fields identify the location of the backend? Server location. Wow. So wait a second. Which of these fields identify the location of the backend? This point looks like server hostname. Just server hostname? What the fuck? Why? So the location of the backend. So the location of the backend. Maybe I'm not understanding what I'm doing. Instance group. What the fuck? Here is not working. This is strange. So is it supposed to not work? Now it's supposed to give me this output. There's something strange with Google Cloud today. Let's see. GCP service status. No major incidents. Okay. So it's not this one, it's not this one, it's not this one. So which of these fields identify the location of the backend, the server hostname and the server location? Okay, because the location may be in one of the different zones in the same region where an instance group has its machines. Now the instance group is related to a zone directly. Therefore, the server hostname and server location. Wow, not clear to me. So we'll just exit from here. Not working as expected, but yeah, we can continue. Configure the internal network load balancer. So configure the internal network load balancer to balance traffic between the two backends, as illustrated in the network diagram. Did we have any other diagram before? No. Oh, yes. Okay, so we have the forwarding rule. Okay. And then we have, perfect. Here. Have quite the same situation. Okay, load balancing. Create load balancer. Type of load balancer. Select network load balancer. Oh, nice. For proxy or pass-through, select pass-through load balancer and click next. Sorry, it was pass-through. Pass-through load balancer, load balance TCP UDP traffic without proxying the traffic to the backends. They preserve the source IP address of the packet. They also support load balancing. Okay. For public facing or internal, select internal. And for create load balance, click configure. Load balancer name will be my load balancer. The region US East 1. And my internal application. Configure the regional backend service. So instance group 1, US East 1 seed, click done. Add a backend. Backend service. Add a backend. For instance group, select instance group 2. Okay. Click done. For health check, create a health check. Name MyLB health check. And will be TCP port 80, check interval 10 seconds and timeout 5. 10 and 5. Health check threshold and healthy 3. Save. So verify that there is a blue check mark next to backend configuration in the cloud console. If there isn't, double check. So then configure the front end, specify the following, and leave the remaining setting as their default. Now, subnetwork, subnet B, right? Yeah, and then create create IP address. But for which one? Internal IP purposes. Create IP address. But what? Where? New front end IP and port protocol IP version subnet. Oh, okay, from here. Let me choose custom IP address. Okay, so we are reserving this IP address under ports for port number type 80. Done. So review. Click create. So last time we created a load balancer, it took a little, like a couple minutes. Therefore, maybe we can check what's next. Test the internal network load balancer. Verify that my ILB IP address forwards traffic to instance group 1 and 2. Access the internal network load balancer. So we go to VM instance, utility VM, we SSH into it, and we curl it. So now it's ready. We can go to the VM. Let's check this one, check my progress. Great. Okay. Now from here, we shall be able to SSH, run this command one time, receive the HTML. Wait. So something is not working as expected. So it says congratulations. Yeah, so we'll just end the lab. Maybe check another time why it wasn't working. Now, okay, we completed this. Let's go to the next activity. Then I will have a research session. Oh, we're 9 now.
Now that we have discussed all the different load balancing services within Google Cloud, let me help you determine which load balancer best meets your needs.
Oh,
One
great.
differentiator between the different Google Cloud load balancers is the support for IPv6 clients. Only the HTTPS, SSL proxy, and TCP proxy load balancing services support IPv6 clients. IPv6 termination for these load balancers enable you to handle IPv6 requests from your users and proxy them over IPv4 to your backends. For example, in this diagram, there is a website, www.example.com, that is translated by Cloud DNS to both an IPv4 and IPv6 address. This allows a desktop user in New York and a mobile user in Iowa to access their load balancer through the IPv4 and IPv6 addresses, respectively. But how does the traffic get to the backends and their IPv4 addresses? Well, the load balancer acts as a reverse proxy, terminates the IPv6 connection, and places the request into an IPv4 connection to a backend. On the reverse path, the load balancer receives the IPv4 response from the backend and places it into the IPv6 connection back to the original client. In other words, configuring IPv6 termination for your load balancer lets your backend instances appear as IPv6 applications to your IPv6 clients. To determine which cloud load balancing products to use, you must first determine what traffic type your load balancers must handle. As a general rule, you would choose an application load balancer when you need a flexible feature set for your applications with HTTPS traffic. You would choose a proxy network load balancer to implement TLS offload, TCP proxy, or support for external load balancing to backends in multiple regions. TLS offload, TCP proxy, or support for external load balancing to backends in multiple regions.
Okay.
You would choose a pass-through network load balancer to prevent client source IP addresses, avoid the overhead of proxies, and to support additional protocols like UDP, ESP, and ICMP, or if you need to expose client IP addresses to your applications. You can further narrow down your choices depending on your application's requirements, whether your application is externally facing or internally facing, or whether you need backends deployed globally or regionally. If you prefer a table over a flowchart, we recommend this summary table. The load balancing scheme is an attribute on the forwarding rule and the backend service of a load balancer and indicates whether the load balancer can be used for internal or external traffic.
So traffic type. So deployment mode is global external, regional external, classic internal, always regional. So then we have a proxy network as a global external, regional, external, internal, and then pass through networks can be only regional, external, internal. In the application load balancer, we receive HTTP and HTTPS traffic, proxy networks, maybe TCP, with optional SSL offload, without SSL offload. Okay, and then we have pass-through network, which works only at regional level. And we have all the, from the external, we receive all the protocols. Not all, but a lot. And then for internal, only TCP and UDP. So network service tier is premium for the major part. Network service tier. Okay, so this is another thing I should research. Mark has completed. Let's see. So which of the following is not a Google Cloud load balancing service? Internal network, SSL, TCP, HTTPS. Yeah, they all exist. Which of the following are applicable auto-scaling policies for managed instance group? CPU utilization, monitoring metrics, load balancing capacity. Which 3 Google Cloud load balancing services support IPv6 clients? Oh, fuck. So only HTTPS. Jesus, we just have seen it here.
Now that we have discussed all the different load balancing services within Google Cloud, let me help you determine which load balancer
HTTPS, SSL, and TCP. Okay, so internal and network, they do not support IPv6 as internally and at level network, we work only with IPv4. Oh, fuck. So, sorry. Which is, to get credit from multiple selection, you must select all of the correct options and none of incorrect ones. So queue-based workload was also correct. Okay. Let's just proceed. So we ended
In
this
this module, we looked at the different types of load balancers
module.
that are available in GCP, along with the managed instance groups and auto scaling. You were able to apply most of the covered services and concepts by working through the 2 labs of this module. We also discussed the criteria for
Now that we've
Okay, so nice arrival point. We are at more than half of this course, and we already did interconnecting networks, load balancing, and auto scaling. Now we miss only infrastructure automation, which I'm curious what's about this. Managed services, great. And course resource, well, it's just the ending. Great, so I'm really happy of what I've achieved today, and in theory we should already have been promoted to the Diamond League. It says 23 minutes remaining. Okay, I'm confident that I will not be surpassed in these 23 minutes, so I will close the video here. Thank you very much for being present today. I'm really happy to continue working, and I hope once a day this will be useful for somebody. Bye bye.